Let's do it. All right, so we're talking about being able to study rotations and describe the motion. We'll get to the cause of acceleration changes in motion, kind of like Newton's laws, but for rotation. We'll also apply energy analysis to rotations. We're going to do that first, which makes a lot of sense. And then we're going to do angular momentum. So it's all similar framework, and that's, when you study it that way, you're good. But you really have to do problems, because it is a lot. It's a lot for everyone. So remember, we're talking about either kind of an object going around on a circular path, or a solid object spinning around one way or the other with an axis of rotation like that, rigid body we call it. Revolutions, angles, and radians, or tangential components, all valid ways to analyze and describe the motion. Let's go over here and remember, so why I encourage you to make sure you can derive the constant acceleration, because they're a really good starting point, and they're quite useful. They aren't the whole game. I mean, in general, we just saw that angular acceleration in, always when you see an equation, look at the units, radians per second, radians per second squared, right? In the derivative form, that can be evaluated at an instant, or you can do delta omega over delta t for an average. Or you can do, over an interval, delta omega is earlier to later. And remember, if you need it, you don't always, that's omega earlier, omega later minus omega earlier is equal to alpha dt. Now, you got to actually do this integral, you need alpha as a function of time. And I can give you any crazy function of time just to do it. Or maybe there's a function that actually describes something useful. So sometimes it's just an exercise, and sometimes it actually is a real application. But if there's a function of time, you can do the derivatives, as messy as you want. If it's constant, we get to pull it out. So that's a special case. Otherwise, we got to put it in there. Now, if I have a graph of alpha versus time, then this would be the graphical area. Or I can look at the average alpha times dt. But it's constant. So let's take a look at the constant case. If constant alpha equals a constant, well, then I could say delta omega is equal to alpha dt, delta t. Because I pulled the alpha out, and the integral dt is delta t. And that tells me that omega later minus omega earlier equals alpha delta t. And a nice form for that, any form works, but this is a very nice form, is that the rate of rotation, radians per second, that I end up with is whatever I started with plus, and this could be positive or negative. Boom. Look familiar? Should, right? Same thing. But notice, radians per second, radian per second squared times second is radians per second. Boom. Now I go to this. Remembering with experience that we start with alpha and work our way backwards. So now, in general, what's true is the rate of travel, rotation, in radians per second is radians per second. Or it's an integral, delta theta is the integral omega dt. If omega is constant, well, that's just equal to omega delta t if omega is constant. But in general, if you have omega as some function, you stick it in there, do it. Or you graph it and look at the graphical area, just like you do integrals. In this case, what we have is alpha equals a constant. So we're going to have delta theta is equal to the integral e later. But now omega is not constant. Because in principle, you're either increasing the rate of rotation or decreasing the rate of rotation. So the function that we put in here is this. We make a little notation shift. You can be a little slower about this than I am, but I'm just going to go, that's omega earlier. What's omega? Omega earlier plus alpha times time. Alpha's constant, in this case, that's the only reason I could use this. You could have different equations here. Omega earlier is just whatever it is. So that's got to be, doesn't change, it's omega at that time. So if you want, you can go through and again go omega earlier, you can split the integral or not split the integral, whatever, and that's omega earlier delta t, if I can pull that out, and plus, well, alpha's constant, integral of t dt is 1/2, so 1/2 alpha, and I'm going to really, and that's a little shift that I'm not going to bother to pin down. And then I have that equation. And once again, when I apply it, I don't use earlier and later, I use 1 and 2, or 2 and 3, or 1 and 3 as my states. If I solve for time here, plug it in and square it, yuck, and then I put it in here, and this, you know what the equation is going to be, right? Omega later squared equals omega earlier squared plus 2 alpha delta theta in radians. Don't forget that we now know degrees don't relate these things. And you've got your case where things are constantly increasing the rate of rotation or constantly slowing down, either really or approximately. And that's rotational kinematics. So do a bunch of problems, and they shouldn't be too bad. Be able to go from revolutions to radians to tangential and back and forth. And you've got this mastered, and we'll move on. So, okay, let's go on.